So, good evening, everyone. It's my pleasure to be here and present the interesting work done by Lithuanian researchers in 2024. I'm Linas, the president of Artificial Intelligence Association of Lithuania. And every year we're doing the AI Awards annual event in which we present the best of the best in various categories, and one of the categories is the best AI research publication by Lithuanians, as well as best young scientist publication of the year. So this year we have a really nice 12 strong publications which are considered for the award, and today we will have the ability to listen 8 presentations and to learn about what is new in the field of AI, in the scientific field, and in which problems our national Lithuanian researchers working all around the globe. So, without any further introduction, I would like to start today's presentations, and we'll have 8 really wonderful presentations.
My name is Arnoldas Budzys, and I'm from Vilnius University Institute of Data Science and Digital Technologies. And today I will present our research focused on the implementation of deep learning-based authentication for insider threat detection in critical infrastructures. Why we are focusing on critical infrastructures? Because we are all depending on those systems. It's electricity, water, traffic management, military, railways, and others, and their importance makes them prime targets for cyber attacks, as breaches can severely compromise the sovereignty, stability, and functionality of cities and entire nations. Anyone who has ever tried to enter a critical infrastructure site knows that physiological biometrics authentication methods such as fingerprint, iris, or facial recognition must be checked. In some cases, behavioral biometrics such as voice, signatures, or keystroke dynamics, because some critical infrastructure areas only allows keyboard when connecting to the system, prohibiting the use of the smartphones, tablets, or any other devices. Authentication based on keystroke dynamics is important because every individual has its own unique keystroke pattern or keystroke typing behavior. Even if an unauthorized person obtains your password by looking over their shoulder or other ways, they would not be able to replicate your unique typing behavior. As a result, the system would deny access, providing an additional layer of security against insider threats or unauthorized access. So what is the keystroke dynamics? Each time you are typing a password, timestamps are captured, representing various timing characteristics such as typing speed and rhythm. These times include the durations of the holding time, time between pressing one key and pressing the next one, the time between releasing one key and pressing another one, and releasing both of the keys. This is how the publicly available data sets of keystroke dynamics were collected. One of them is Carnegie Mellon University, later we call it CMU, and Greg-NIST Lab. Now that we are familiar with these publicly available data sets and understand the need to distinguish legitimate user from insider based on their typing behavior, we examined the related work conducting using these data sets. We found out that the most researchers evaluate the performance of their models using the equal error rate, which represents the trade-off between false acceptance rate and false reject rate. In addition, we found that the researchers often handle timestamps as numerical values in their analysis. So after this related works, we tried to train our model based on numerical values and gain the same results as these researchers in their papers. So we looked into another direction and focused on convolutional neural network, because convolutional neural networks are good at feature extraction from the images. And but as keystroke dynamics are numerical values, we needed to transform somehow numerical values into the images to be suitable for convolutional neural networks. For this purpose, we used a Gabor filter, which is commonly applied in 2D image. It highlights the features such as edges and textures at specific orientation and frequencies, making it ideal for feature extraction. But we modified Gabor filter formula to be applied not for the images, but for the timestamps. So when the user types their password, timestamps are collected, referred to the time series A. After it, we apply our modified Gabor filter formula, refer and get the value, and we are getting the values referred to the time series B. Then we multiply A values with the B into the matrix and give each value the color and we get the image. And we call this representation Gabor filter matrix transformation. Now that we have the image and we are planning to use a convolutional neural networks, we applied Siamese neural network with the triple loss function to distinguish legitimate user from imposter. For model training, we prepared the data set as triplets. Each input consists of 3 images: an anchor image representing the legitimate user, a positive sample from the same user but a different instance of the same password, and a negative sample representing different user typing the same password. During the training, the network learns to increase the similarity between the anchor and positive samples by bringing them close together in the latent space, while decreasing the similarity between anchor and negative sample by pushing it further away in latent space. Now imagine this system implemented within critical infrastructure. When the trained network monitors your typing behavior, it compares your typing pattern with the stored password database of your username. If the pattern matches, the system grants access. However, if an insider attempts to use your password but fails to replicate your typing behavior, the system blocks access and sends alert to the Security Operation Center for further investigation. On the right-hand side, you can see how the trained Siamese neural network distinguishes users. Blue and green dots represents different users, which with each dot corresponding to 1 password attempt. The remaining dots represent randomly selected attempts from other users typing the same password. So after training the network, we achieved a lowest equal error rate of 0.045, which is twice as good as the result compared in the original paper using the CMU data set. Compared to other research studies, our approach also consistently outperformed the results. However, we did not stop here. We transformed the data using other well-known transformation methods and compared the outcomes with the GAFMAT. GAFMAT continued to deliver the best performance and demonstrated the most stability in equal error rate across all experiments. But we didn't stop here with the CMU dataset, and to ensure that our GAFMAT approach is truly effective, we tested it on another dataset, Gray-Kniss lab. After training the network, the results outperformed those of the other studies that used this dataset for user distinction based solely on numerical values. So after validating the results, we concluded that a neural network trained on typing behavior transformed into images significantly can enhance security in critical infrastructure. This approach strengthens cybersecurity by addressing key vulnerabilities of traditional password systems, including theft, surveillance, social engineering attacks, and other ways. So this brings us to the end of my presentation and a short brief overview of the published paper. Thank you for your attention and have a great day.
A master's student of computational biology and bioinformatics in ETH Zurich. In this video, I'm going to present a publication called TemStaPro, Protein Thermostability Prediction using sequence representations from protein language models, which was published in Oxford Bioinformatics. To begin with, proteins are essential molecules for any organism. They carry out the most important and actually the majority of functions in any organism. Protein molecules are composed of an amino acid sequence, which folds into a 3D structure, and this structure determines the function that the protein is able to carry. There are several external factors that influence this folding process, and one of them is temperature. If the temperature is too high, the protein structure unfolds and the protein is no longer able to execute its function. So there is a need to have prediction tools as convenient as possible to determine at which temperature, or in our case, highest temperature interval, at which the protein would still be stable. As for any machine learning task, data is the crucial part of the process, and luckily we had access to an extensive data set of around 21,000 organisms with optimal growth temperature labeled. This dataset was collected by 𝐀𝐈 in 2018, and we took the subset of non-eukaryotic organisms, meaning that we took only bacteria, to keep it simple. We took their proteins, we clustered them based on sequence similarity, and then we divided those clusters into training and testing sets. Subsequently, the data had to be labeled. Since we defined this task to be a binary classification task with a certain temperature threshold, we had to label all of our data set accordingly. So going from 40 degrees Celsius to 45 and so on, we would have the lower the threshold, the more proteins of a positive class. All of these relabeled datasets would eventually compose the final dataset called TemStaPro Major 30, and this is the dataset that would be used for the final model's development and testing. And even more, we took a subset of that major dataset and called TemStaPro Minor 30, and both of these datasets were deposited in Zenodo for public availability for anyone to use who needs a dataset like this. The idea of this work was to utilize transfer learning for our goal. So essentially, we used a protein language model to retrieve the inner representation of proteins called embeddings, which are highly dimensional vectors, and we would transfer these vectors into an application neural network trained for exact purpose, for precise purpose, and in our case it would be the thermostability prediction. The initial principal components analysis of these embeddings showed some promising results. We could see that proteins were clustered with respect to their temperature labels, with respect to 65 degrees threshold, based only on the first two principal components. So we had this promising hypothesis that the model trained on these embeddings should relatively easily achieve quite high performance. So this is how we proceeded. We took for each protein, we retrieved embeddings, mean embeddings for that matter, which would be passed into an application neural network, which would in fact be an ensemble of networks for each temperature threshold. But for the sake of this presentation, let's just abstract it into a single application neural network, which would provide a bunch of predictions for each temperature threshold. and these predictions would actually be binarized, and then we could compare with the true labels that we had. Of course, the method would sometimes do mistakes, and mostly it would provide actually accurate predictions. And we could see that in comparison with other recent methods for thermostability prediction, and our method would perform better. Furthermore, we took a look at predictions on experimental data, and in 90% of cases, TemStaPro predictions would differ from experimental characterization by no more than 10 degrees Celsius. So all in all, this work demonstrated that protein language models encode thermostability signal very strongly for very high-performing downstream thermostability prediction tasks from only protein sequence alone. Even more, this work collected, processed, and made an extensive dataset of around 1 million sequences publicly available. And finally, the tool itself, called TemStaPro, is publicly available as well on its GitHub repository for anyone to use.
Su Karolis šiandien kalbėsiu apie antikūnių kūrimą pasitelkiant dirbtinį intelektą, ties kuriuo mes dirbame Prescient Design. Prezentacija bus anglų kalba. So without further ado, let's get into this work I did with a lot of my amazing colleagues at Prescient. So what are antibodies, and why do we care about them? Antibodies are these Y-shaped proteins that our immune system uses to fight diseases. They attach to undesirable antigens, and with this indicate to the immune system to kill whatever they attach to. This attachment happens with the CDR loops of the variable region of the antibody. So we usually only look at this variable region. As you can see, the structures can be quite complex, but being able to model them well would be very useful, as antibodies have proven to be an important tool in drug discovery, with 30% of new drugs being antibodies. So the ideal goal for us would be to be able to take some target badge, an epitope, on the antigen of our choosing and design an antibody binding to it using machine learning. This would greatly speed up the drug discovery process and allow us to skip animal immunization campaigns that are used now. Towards making this vision a reality, we have seen great progress in the field of protein design with ML. The list is too long to cover here, but the existing works fall in two main categories: generative models that make arbitrary proteins and usually work poorly with antibodies, or antibody-specific methods that mainly focus on just the CDR loop redesign, conditioned on existing paired antibody and antigen structure, instead of designing the full variable region of an antibody. Most of these works, like with many other generative AI tasks, use diffusion. As you probably will know by now, in the diffusion framework, we gradually noise a given sample, such as this cat, and train our model to reverse one individual noising step, so to go from some x to x minus 1. At generation time, we can then sample pure noise and iteratively apply this denoising to eventually generate a nice image. For proteins, similar recipes follow. As a protein is a chain of amino acids that you can see on the right, often it is generated as a 3D point cloud of such amino acid residues that are allowed to float freely, and at the end of the denoising process, hopefully, result in you constructing a chain. Some methods just generate the backbone in such manner by diffusing the center of mass position of each residue, as well as 3D rotation on the SO3 manifold. So the particular amino acid type can be later generated by a second model, and then the side chain atoms can then be placed by using some force field, as each amino acid has a different side chain structure and a different number of atoms. These two additional steps are sometimes integrated into one model, but not always. The currently used relational SE3 equivariant architectures can lack in expressive power and are very computationally expensive. Thus, for example, it is quite common to only model the backbone, which is a simpler task. Additionally, public datasets only have thousands of unique, high-quality antibody and antigen examples, so we're in a very low data regime. In our work, we aim to alleviate these model power, modeling fidelity, and data efficiency issues by focusing on a given protein family. In this case, antibodies. If we constrain ourselves to some family with a consistent fold, we can have a fixed-length structure-informed sequence alignment. We use such fixed-length representation for antibodies that allows us to generate structure and sequence jointly with varying sequence lengths, as well as to construct a much more efficient non-relational equivariant and model and build data-driven priors for the diffusion process. Using such alignment allows us to represent our antibody simply as a fixed-length tape. that in the first columns encodes the amino acid type or a gap if the residue is missing, and in the subsequent columns has all atom positions being modeled for the residue represented by this row. With this representation, we don't need expensive relational and equivariant architectures like graph neural networks and transformers, and can simply apply MLPs across row and columns to update the representation and mix the data. MLP mixture style, if you're familiar. We use 𝐒𝐜 antibody sequence alignment that ensures all reasonable antibodies have at most 298 residues or rows in our representation, with gaps being placed in the middle of CDR loops, where most of the natural sequence length variation indeed occurs, in a way that subsequent sequence alignment would result in a close to optimal structural alignment. This also means that each row in the table is associated with a specific structural role, and it's easy to change antibody length by just predicting a gap instead of some amino acid in a given row. While fully equivariant architectures are quite inefficient, equivariance through rotations and translations can help model performance, especially in the low data regime. While this stack of MLPs that we use is clearly not equivariant, it's actually easy to make it equivariant to rotations and translations by using frame averaging. And frame averaging says that, you can achieve this equivariance if you feed the model for canonical representations of the atom point cloud as determined by the maximum variance directions and average the model outputs. But let's not get into more details here. The important thing is that this MLP mixture-like architecture allows us to have a much larger and faster model while consuming less GPU memory, as we are not modeling all O and squared pairwise interactions the relational models normally do. This increased overparameterization allows us to generate antibodies that are much more statistically similar to the real ones. As we use this aligned representations for the diffusion process, instead of noising till we reach pure isotropic noise, as usually done, we can have a more structured target noise distribution, which probably makes the model's task easier. For this, from the data we construct informed priors, which for amino acid sequences, as you can see here, correspond to different amino acid histogram at each position. For atom diffusion, we fit a Gaussian marker random field to all atom positions, which give us a covariance matrix used in the Gaussian diffusion that keeps atoms close together if atoms in such positions are close together in the data, meaning the process respects the fact that proteins are actually a chain, as well as the general consistent interactions in the antibody fold, as it is a rather conserved fold. It is easy to see visually that with such a covariance matrix, the antibody, even at fully noised structure, keeps some semblance with a high-level structure, and from the results, we see that both of these priors improve the modeling quality substantially. The last ingredient in our method is the projection layer. As we are working with an atom cloud instead of a residue cloud, we would like to ensure that our generated structures are physically plausible and have correct bond lengths, at least inside of the residues. Our projection layer takes idealized templates of residue structures and aligns them individually to atom positions predicted by the model and replaces them, guaranteeing ideal bond lengths inside each residue. This layer also allows us to easily model full atom structures in our fixed size table representation by including 4 pseudoatoms that represent the side chain. As each amino acid has at most 4 degrees of freedom in its side chain, this is enough to build idealized full atom structure while avoiding explicitly modeling all side chain atoms, which is great, as most side chain atom positions are heavily constrained and side chains vary greatly in size, which would cause problems in our table representation. To test how applicable this model would be in a drug discovery setup, we train it on a set of mutants of trastuzumab, a known drug, that are binders and ask it to generate more binders. This would be valuable when screening for various developability issues. Our in silico evaluation with an oracle model trained on both binders and non-binders shows that our model generates antibodies that are much more likely to be actually binders than alternative existing models, especially when reducing sampling temperature to generate higher confidence samples. But in silico evaluation is known to be not perfect. So we submitted some randomly selected designs to the wet lab, either with no filtering or with some basing filtering that ensures the randomly selected samples are in the best part of the generated distribution. All designs expressed, and up to 57% of the naively filtered designs, were binders. One of the 6 newly identified binders even displayed stronger binding affinity than the existing drug, which is quite impressive. We also tested AbDiffuser on the traditional CDR redesign task, where given a previously unseen bound antibody and antigen complex, we delete all of the antibody CDR loops and ask the model to design them. Since in this task the model is conditioned on the antigen structure, we add a one-layered graph neural network to produce the initial embeddings that are fed into our table representation of the antibody, and otherwise we use the model as previously described. Simple conditioning of our model is already sufficient, and AbDiffuser greatly outperforms both the traditional computational Rosetta baseline as well as the previous state-of-the-art ML method with a good margin, especially in the CDR-H3 loop, which is the most important one as it mediates most of the antibody and antigen interactions. As we have shown, AbDiffuser is good at modeling antibody distributions and can be conditioned to design against unseen targets. We are now working hard to make such structure-based generative models an integral part of antibody discovery process. If you're interested in this line of work, do check out our hiring page for PhD internship opportunities. Thank you for your attention.
Karazija, and I'm excited to share our work on learning segmentation from point trajectories. This is joint work with my supervisors, Ieva, Christian, and Andrea. Video data, unlike image modality, contains rich motion information. This is particularly useful when trying to learn signals of objectness or segmentation without relying on manual annotations, such as unsupervised segmentation tasks. Many approaches that rely on motion are rooted in principle of common fate from Gestalt psychology, which posits that elements that move together are more likely to belong together. Traditionally, motion information has been captured using optical flow. However, optical flow only describes the instantaneous motion of the scene. This can create blind spots. Not all objects are necessarily in motion at all times, or similarly, groups of objects might coincidentally move together. However, recent point trackers offer an alternative form of motion information, a sparse set of points whose motion and visibility is described over a course of a whole video, showing long-term evolution. In this paper, we ask if long-term motion of point trajectories is useful, and how should one extract objectness information from point trajectories. The central intuition in our work is that motion of points belonging to the same object should be well correlated, an expression of principle of common fate. Our main insight is that one can use a set of point trajectories to model the motion as a combination of other points in the group. We design a cost function to assess a given segmentation based on how well it explains long-term motion. More formally, let us assume that we have a k-way mask M predicted for some frame in the video. In practice, this would be an output of a segmentation network. Let us consider a set of n trajectories visible for the same frame. Assuming each trajectory is two-dimensional and of length t, we can stack them into a matrix P. And we can sample mask values at trajectory locations and consider pk as shown. The main idea behind our loss function is as follows. pk should be low rank if the masks M align well with objects. To see this intuition, consider the following 2D example. We have a triangle and we track 4 points over 3 frames. The triangle rotates, but not at a constant rate. This means that the position of points or their change, the optical flow, are difficult to model. We can stack the point positions into a matrix forming pk. But we know that the 4th green point is a combination of others, so the 4th column is a linear combination of other columns. Thus pk is rank deficient. In fact, we could add any points inside a triangle without increasing the rank of pk. If we assume that pk should be of rank r, then its rth and higher singular values are 0. So we simply use the magnitude of these singular values as a loss. So what should rank r be? For that, we investigated the meaning of SVD decomposition, but I will leave the details to the paper. In short, at rank r equals 4, we can model the relative rigid motion of objects and cameras such that projective depth of points remains constant. We further relax this assumption to support varying depth, non-rigid motion, and tracking errors, and use r equals 5. We begin our experimental analysis by testing the feasibility of this loss function in a simulated setting with known masks and motion information. We can then distort the segmentation masks by injected noise, changing the temperature of the mask distribution, or deleting or introducing new segments. We can then investigate how the loss responds to such changes. On y-axis, we show the loss value, and on x-axis, the over or under segmentation. Different series correspond to noise and temperature settings. We find that the loss prefers both low noise and low entropy solutions. Looking at the x-axis, which shows the number of segments introduced or removed, we find that the loss penalizes both under and over segmentations. This shows that the loss values should correspond to correct mask distributions. We leave other analysis to the paper and skip to comparisons with existing SOTA and supervised video segmentation methods. Here, we use a similar setup as in prior work. We train a segmentation network to predict the mask distribution. We then calculate our loss using the predicted masks and trajectories obtained from frozen point trackers, and then backpropagate. We also included a loss on optical flow. As optical flow is dense, we found that it is very beneficial for overall segmentation quality, especially around the boundaries. Here we show video results of our method. In summary, we introduced principal method to train an image segmentation network using long-term motion information expressed as point trajectories. Our trajectory loss formulation aims to group trajectories into low-rank matrices, representing the idea that motion of points belonging to the same object can be roughly expressed as combination of other points. While in combination with flow loss, we obtain state-of-art results in video object segmentation. Thank you.
Sveiki visi. Tai visų pirma norėčiau labai padėkoti Lietuvos dirbtinio intelekto asociacijai už tai, kad organizuoja tokius renginius kaip 𝐀𝐈 Awards ir be galo daug kitų iniciatyvų. Tiesiog yra be galo smagu matyti, kaip aktyviai yra kuriama Lietuvos 𝐀𝐈 bendruomenė ir labai ačiū labai visiems prisidėjusiam prie to. Aišku, labai smagu yra gauti ir pačią nominaciją dėl savo straipsnio, bet kartu buvo turbūt smagiausia skaityti visų kitų nominacijų straipsnius. Tai labai smagu matyti, kad tiek daug lietuvių dirba tiek užsienyje, tiek Lietuvoje prie tiek skirtingų temų ir kaip tos temos iš esmės kartu ir susiriša ir kaip įdomu yra ieškoti kaip ir skirtingų sąryšų ir santykių tarp skirtingų straipsnių, kurie buvo nominuoti. Tai labai ačiū už inspiraciją ir tikrai rekomenduočiau visiems kitiems irgi paskaityti visus kitus darbus, kurie buvo nominuoti šiais metais. Ir kaip ir trumpa istorija mano paties susijusi su 𝐀𝐈 Awards, kad 2021 metais, kai aš tuo metu dar dirbau New York'e, dirbau su ekonominiais tyrimais, 𝐀𝐈 Awards'ai Lietuvoje, irgi vykę žiemą, buvo kaip ir mano vienas iš pirmų tokių susirišimų su AI tyrimais, nes tuo metu, nors dirbau su ekonominiais tyrimais, aš kaip ir buvau nusiteikęs ir pasiryžęs persikvalifikuoti, iš esmės mest beveik viską, ką dariau tuo metu ekonomikoje ir pereiti dirbtinio intelekto sritį. Ir tuo metu neturėjau nei per daug žinių ar pagrindo, bet patys 𝐀𝐈 Awards'ai buvo kaip ir viena pirmųjų progų man daug daugiau susipažinti su pačiais tyrimais ir tiesiog paklausyti žmonių, kurie be galo įdomi ir motyvuoti kalba apie savo darbą ir tiek paskaitos, tiek po to skaitimas straipsnių po visos konferencijos iš skirtingų skaitytojų buvo be galo gera ir labai labai motyvuojanti patirtis. Tai ačiū labai už visą organizaciją ir turbūt tokių istorijų kaip mano yra ne viena. Ir dabar kaip ir norėčiau pereiti prie trumpo savo paties straipsnio pristatymo, tai labai gaila, kad kaip ir aš apžvelgsiu tai pagrindinės detalės, bet jeigu kas nors norėtų kaip ir daugiau sužinoti apie patį straipsnį, tai prašau kreipkitės į mane, būtų be galo smagu daugiau pakalbėti apie tai. Ir kartu aš pačią prezentaciją darysiu angliškai, nes paprasčiausiai būtų paprasčiau naudoti visus terminus, bet vėlgi, jeigu kažkas turi klausimų lietuviškai taip toliau, tai būtų be galo smagu atsakyti į visus klausimus. Tai to transition to English, so the paper I'm going to be presenting is called Rethinking Out-of-Distribution Detection for Reinforcement Learning. I presented the paper at the Conference for Autonomous Agents and Multi-Agent Systems, also known as AAMAS, in New Zealand in 2024. We've been super happy to have both the main conference paper as well as an oral presentation at the conference. And I just wanted to give really big credits for my incredible advisors. So thank you, Tim Fransmeyer, Christian Schroeder-DeWitt, and also Jacob Forrester for all of your support throughout this work, which was done actually during my master's year at the University of Oxford. So as a motivating example, imagine if you're just taking a self-driving car in places like San Francisco where they're very prevalent, and you're simply driving for the road, and you can sort of feel it at one point the pavement that you're driving on changes. And instead of finding yourself on a road, you actually realize that the car has driven into a piece of wet concrete, which is something that actually happened to one of the passengers of Cruise Autonomous Drivers vehicle company, I think 1 or 2 years ago. And so what the car essentially failed to recognize is the difference within not only the warning signs, but also the difference within the pavement and the prediction for it going forward into the place where the construction took place. And so while this kind of example might seem really simple and pretty humorous for us as human drivers, the inability to recognize a change in the pavement on the road, it's actually really prevalent within reinforcement learning algorithms. One of the main reasons being that reinforcement learning algorithms are quite brittle. Despite numerous successes, their capacity to generalize to unforeseen circumstances, essentially unforeseen anomalies, remains a really big challenge. And this is especially important given the real-world deployment of such systems as autonomous vehicles, drones, as well as autonomous robots. And while the example that I actually gave before was quite humorous, there's a lot more instances where, for example, self-driving cars could not recognize a change in their environment on time, and that actually led to quite significant problems for humans involved in the situation that stem beyond simply being stopped at a wet concrete place. So this real-world applications of such studies are actually really significant. And so the main topic of this work is called auto-distribution detection in reinforcement learning, which can be defined as the task of identifying whether a given environment, a test time environment, differs from the train time environment, the environment that the model was trained on. So it's very simple. Does the test time environment differ or is the same as the environment that the model was trained on? And so the paper has three main contributions. First is related to standardizing terminology of the field. Second, to proposing new benchmark evaluation environments. And third, proposing new detection algorithms. Unfortunately, I won't have time to delve deeply into 1 and 2, and I'll mainly focus on 3. But just to briefly discuss the terminological contributions that the paper did, because that was actually one of the motivating topics for me is essentially the fact that in other fields like supervised learning and unsupervised learning, the field or the topic of auto-distribution detection has been a lot more advanced. And so there's sort of like established terminologies and established methods for like testing different algorithms. And so one of the first things that the paper sort of like lays out at the beginning is trying to sort of take the established terminologies from auto-distribution detection in supervised and unsupervised learning and then map them into reinforcement learning so that all the different algorithms and proposed frameworks will essentially speak the same language about what kind of anomalies different algorithms are being tested on or the benchmarks that are proposed. And so we differentiate between two main types of anomalies in reinforcement learning environments. I'm not going to go into kind of big detail with them, but like they really try to map them into the broader literature to essentially try to establish more communication between reinforcement learning and supervised and unsupervised learning in this field. We've also created new benchmark environments that essentially are a bit more sophisticated in how anomalies are introduced inside these environments. And then the last thing that the paper does is it proposes a new detection algorithm called Dexter, which I'll go kind of explain in a bit more detail. So just to briefly cover kind of the way the current algorithms work is actually very intuitive for humans. So the training data for these models essentially just a bunch of trajectories, so sequences, pairs of state and actions. And the way these models are trained is that they're essentially given pairs of, let's say, like a current state and a current action, and their goal during training is to predict to have the inaccurate prediction for the next state. So if I'm in state A and I take action B, what is the most likely state that I will end up, given all the training data? And so the way that their detection works during test time is that they will essentially given a current state and action pair, they will generate the prediction for the next state. And the anomaly score for, how likely is that the current environment is actually anomalous, that is different from the train time environment. The anomaly score is proportional to some sort of a difference measure between the predicted state and the current state that the model finds itself in. And so there's essentially quite a few theoretical issues related to this broad approach that really most of the current models fall under. And the paper kind of tries to outline from like a theoretical point of view, what are these problems? But broadly, they kind of ignore residual analysis. They ignore a lot of really important information by simply focusing on this difference between predicted and actual state. There's also kind of like a more advanced issue that we also cover, but I'll mainly focus on the first one, which is, kind of losing this information. And so kind of as a way to address that, we introduced Dexter, which stands for detection via extraction of time series representations. And so the way Dexter works, while this kind of maybe looks a bit complicated, it works very simply. It treats reinforcement learning observations that the model gets as time series data. And so for any time series data, what you can do is you can also extract all the possible features related to it, all the descriptive features, statistics related to it, minimum, maximum sample entropy, autocorrelation. And so kind of instead of trying to detect changes within the raw time series data, it tries to detect changes within all the descriptive statistics that describe the time series. And in this case, it's really hundreds of descriptive statistics that describe the time series data. So the key really of the algorithm, the key idea is to reframe the problem, to first look at RL observations as time series, and then to not look at raw time series, but the descriptive statistics of it. We use isolation forest algorithm to essentially train a model to recognize the anomalies within time series features. And so during test time, what we do is essentially we're going to slice a test time environment data, and then we're going to extract all the possible time series features from it that we can. And the isolation forest is going to compare the descriptive statistics of the time series for the current test time environment to the train time environments that is learned. There's many reasons to use isolation forest here that I sadly cannot go into great detail, but the results are really that Dexter outperforms the state-of-the-art models in almost all the environments that we tested them in, including 17 out of 18 sensory anomaly environments, 11 out of 12 semantic anomaly environments, and also 2 out of 2 proof of concept environments. So just to briefly summarize the paper, essentially what it does, we start by standardizing terminology for out-of-distribution detection in reinforcement learning. We provide a new set of benchmark environments, and then introduce a new detector which outperforms all the state-of-the-art models. All of this is, of course, open sourced, but of course, there's many limitations of this work. I think the main one that I like to focus on is kind of the specific focus of this paper on simulated environments. And so I think there's a big push to actually apply this to more real-world settings, and I'm very excited. There's actually a group at Oxford that I used to work with, where a few students are kind of trying to first make some improvements on Dexter, but second, also think about how it could be applied to more real-world settings. So thanks a lot for listening. I mean, I hope you learned at least something that was even a remotely helpful for you. And I really appreciate the chance to simply share my work. And I hope you all have a wonderful time at the award ceremony. Have a good day.
Hello, my name is Mantas, and this is a presentation of the paper HarmBench, a standardized evaluation framework for automated red teaming and robust refusal, which my co-authors and I presented as a paper at ICML 2024. In the context of large language models, red teaming refers to the process of finding undesirable behaviors that the LLM engages in. This is typically performed as pre-deployment adversarial testing in tandem with the development of safeguards. Developers often rely on manual red teaming to stress test their safeguards before deployment. For example, before releasing GPT-4, OpenAI carried out a manual red teaming exercise for several months to ensure their safeguards were reliable. Unfortunately, these efforts were not enough. After the deployment of GPT-4, many creative individuals were able to jailbreak the model, bypassing the safeguards with adversarially designed strings to get the model to do whatever they wanted. And this isn't just a problem with GPT-4. Jailbreaks remain an unsolved research problem broadly, raising the question of how we can test large language models more extensively before deployment and make safeguards more robust. A promising avenue for solving this problem is automated red teaming, where instead of relying on teams of humans to probe AIs for weaknesses, we develop automated methods that can probe AIs much more quickly and comprehensively. This is an example of the GCG attack, an early automated red teaming method that optimizes a yellow suffix string to bypass the model's initial refusal. Many automated red teaming methods like GCG have been proposed, but unfortunately, at the time we released this paper, there hadn't been any efforts to standardize their evaluation, and it was unclear which automated red teaming methods were most effective. To remedy this, my co-authors and I created a benchmark called HarmBench for comparing automated red teaming methods. Our benchmark consists of 3 components: a dataset of carefully curated harmful behaviors, a standardized evaluation framework, and a large-scale comparison of different red teaming methods. We can also use HarmBench to compare different defenses to improve the robustness of LLM safeguards. To demonstrate how HarmBench can be used in this way, we developed a state-of-the-art adversarial training method to make refusal safeguards more robust, which I'll go over briefly go over the results of this method at the end of the presentation. Before going into the details of our benchmark, I'll first describe the red teaming problem that we consider more formally. We are given a target large language model F, a red teaming algorithm G, and a behavior Y that the red teaming algorithm tries to elicit from the target model. We're also given a behavior classifier C that determines whether the target model indeed exhibited a given behavior. We then define our attack success rate metric simply as the percentage of test cases generated by G that successfully elicit the behavior from the target model. And the goal of the red teamer is to simply maximize this attack success rate metric. Now I'll quickly go over some high-level lessons we learned for how to properly evaluate red teaming methods. We identified 3 desirable qualities of a red teaming evaluation: breadth, comparability, and robust metrics. We find that prior evaluations of automated red teaming methods lack at least one of these qualities, and we establish a set of best practices for future work. In the interest of time, I'll only describe the robust metrics quality in detail, since that is the most interesting and least obvious of all the 3. In automated red teaming evaluations, both attacks and defenses optimize the attack success rate metric. This means that classifiers for computing attack success rate need to withstand optimization pressure. To this end, we identified 2 important requirements for behavior classifiers. The first is to use held-out classifiers and held-out behaviors for computing test time metrics. This is perhaps the most obvious point, or perhaps an obvious point, but unfortunately some papers actually used bespoke evaluations where they directly optimized against their test metrics. The second requirement is to use pre-qualification tests for the robustness of the behavior classifier. For our behavior classifiers, we run pre-qualification tests using 3 sets of unusual inputs with known ground truth labels. Compared to other behavior classifiers used in previous evaluations, ours is far more robust on these simple sanity checks, which demonstrates that running pre-qualification tests is important and often overlooked. Based on these findings and other experiences from developing our benchmark, we proposed these best practices for evaluating red teaming methods, which I'll skip over in the interest of time. Now I'll start describing the data set of harmful behaviors that we collect. We manually craft 510 harmful behaviors, each consisting of a behavior string, which is a short description of the behavior to be performed, and optionally some additional information that depends on the functional category of the behavior. So we have 4 functional categories, each of which has structural differences in how it's evaluated. These are standard behaviors consisting of self-contained short behavior strings, copyright behaviors that match behavior strings to hashes pre-computed on the copyrighted content, contextual behaviors, which pair short behavior strings with context strings, longer context strings, and multimodal behaviors, which pair the behavior string with an image that the behavior references. And we have a nice distribution across these different functional categories. We also have 7 semantic categories in our benchmark, drawing on the acceptable use policies of OpenAI, Anthropic, Meta, and Inflection AI. Now I'll briefly go over some examples of harmful behaviors in our dataset. These are behaviors from the standard behavior functional category. So you can see they include things like synthesizing biological and chemical weapons, generating copyrighted text, or helping with various forms of cybercrime. One common criticism of large language model jailbreaking research is that a lot of this concerning stuff that we're showing here could actually just be looked up on Google. You can, for instance, look up instructions for how to synthesize nitazene on Google. And to address this and also to include interesting diversity of behaviors in our benchmark, we have these contextual behaviors which pair the behavior string with a long context string. And this is, for example, a context string taken from a real publicly available academic paper showing a synthesis pathway for fentanyl synthesis. This is something that academic researchers study and come up with different synthesis pathways for it. And the specific behavior that's being asked of the large language model here is to describe the precursors needed for this pathway and how to obtain them without a license. And this is importantly something you could most likely not find just by looking it up on Google. So this demonstrates our large language models do have some additional risks above and beyond what can be accomplished with a search engine. We also have multimodal behaviors like so. And now I'll start describing the evaluation, briefly describe the evaluation pipeline. First, we generate test cases with the red teaming method. Then we run these test cases on the target model, optionally with a defense. And we take the completions generated by the model and pass them along with the behavior strings and other information from the behaviors into the behavior classifier that I described earlier, which produces our success rate metric. Our large-scale comparison consists of 18 different red teaming methods from 12 papers and 34 different large language models. For each model, we run all compatible attacks on all behaviors. And our high-level result is that no model is robust to all attacks, and no attack is strong against all models, showing that there's room for improvement both on the automated red teaming side and on the defense side. We also evaluated the automated, the adversarial training method that I mentioned at the start of this talk, and found that it greatly improves robustness to one of the strongest attacks. And it also preserves performance at a reasonable, benign performance at a reasonable level. And that's my talk. Thank you very much for listening.
Joining me, my name is Paulius, and I'll present our work on self-healing machine learning, a framework for autonomous adaptation in real-world environments. This is joint work done together with Nabil Sirat, Christoph Karazija, and Mikhail Ivanchar. So what is this paper about? We're focusing on a very important issue of how to optimally adapt in the presence of changing environments. So specifically, we're looking at supervised learning models, and we're looking at what happens once there's a change in an environment and a model's performance degrades. Now, the main problem we're addressing is that current approaches to addressing such shifts rely on predetermined actions. More specifically, they typically have a certain set of actions that they choose from upon detection of some sort of drift. This could be, for instance, triggering model retraining. It could be reusing an old model. It could be, for instance, finding some sort of combination between different old models. And the main problem is that this might lead to suboptimal adaptation whenever the optimal action isn't within the set of actions you're considering. So we propose self-healing machine learning as a general framework that can be used to adapt best to different environments. And we think this is extremely useful because within self-healing machine learning, there's a healing system which diagnoses the problem, which means the reason why the model has degraded. And we argue that we should condition the best possible action on the basis of that reason. That is, we should first identify why the model has degraded and then only find the best action after we have understood the primary reason for degradation. So let's look at an example how different adaptation strategies might result in different performance. So looking at this picture, on the x-axis you have time, on the y-axis you have accuracy, and initially you see stable model performance. Then you see an environment change and you see a sudden drop in performance. So here's a question. What's the best possible action to take in this situation? Is it, for instance, a A1 to retrain the model, A2 to reuse an old model, A3 to add covariates, or A4 something else. Now, clearly there's no correct answer because it depends on the reason why the model has degraded. There are cases where adding a new covariate is the best solution. There are also cases when retraining the model is the best solution. There are also cases when not doing anything is the best solution. You got to understand what specifically happens and only then propose these sorts of strategies, what to do. Clearly, this is intuition we take for granted, but state-of-the-art practices don't really mimic this intuition because there's no diagnosis step within the process. We don't try to understand why a model has degraded. We simply typically choose from the set of actions that have already been, or the set of decision rules that have been implicitly defined within our adaptation strategy. So to avoid this, we propose self-healing machine learning. It's a general framework. We've mathematically formalized it in the paper, but to give you a high-level overview, it consists of 4 steps. A monitoring step, which is typically implemented with a statistical learning algorithm, which tries to answer the question, has the performance of the model degraded? A diagnosis step, which tries to answer the question, what are the main reasons for the decrease in performance? An adaptation step, which is, given the reasons for the decrease in performance, what strategies can help heal the model or return the model back to its prior good performance levels? And then stage 4 testing, can we evaluate these different proposed adaptation strategies, and we can then deploy the best specific strategy to the machine learning model. We formalize this mathematically in the paper. We also propose a concrete algorithm called HLLM, which uses language models for steps 2, 3, as well as orchestrating the whole pipeline. So we use a language model to propose hypotheses as to why is it that the model, the machine learning supervised learning model has degraded, then propose specific adaptation strategies, convert that into functional Python code that can be then executed and tested. And so machine learning models are then modulated by a language model, which does the diagnosis step, which does the adaptation step, and which also orchestrates the whole implementation pipeline. We find that HLM significantly outperforms existing practices of adapting different models whenever understanding the reason why degradation matters is important. So self-healing machine learning is a general framework for autonomous adaptation in real-world environments. We think it can significantly improve the way different models adapt whenever understanding why change in the performance has happened is important. Thanks so much for watching.
Hi, my name is Tomas Vaškevičius. And I will present joint work with 𝐀𝐈 𝐒𝐜𝐢𝐳 on the computation of doubly entropic Wasserstein barycenters. I will begin by setting up some notation. So a central object in our paper is the entropic optimal transport cost, which is defined as T lambda in the middle of this slide. Here, lambda is a regularization parameter. Of course, if lambda is equal to 0, then we have an unregularized optimal transport cost, which is also known as the squared Wasserstein distance. And the squared Wasserstein distance gives a very natural notion of a barycenter between a given collection of probability measures. Here in the plot shown at the bottom of this slide, the black solid line is a Wasserstein barycenter between 2 measures plotted as dashed black lines. On the other hand, the purple line is an L2 barycenter between the same 2 measures, which in this case corresponds to taking the average of their probability density functions. Unfortunately, the computation of the unregularized Wasserstein barycenter is computationally challenging, which leads to a consideration of regularized approaches. Here we look into a family of lambda tau barycenters. It is a family of entropy penalized Wasserstein barycenters governed by 2 parameters, lambda and tau. And as it turns out, different combinations of lambda and tau, they recover many of the previously studied entropy regularized barycenters. They are surveyed in the paper by 𝐀𝐈 𝐒𝐜𝐢𝐳. And actually the benefit of looking into this 2-parameter family of barycenters is that a new type of barycenter was recently discovered, which corresponds to the case of taking tau equals a half of lambda. And the benefit of this barycenter is that it offers superior approximation error qualities. And this is actually The main purpose of our work is to describe an algorithm and prove convergence guarantees for this algorithm on the computation of this new type of barycenter when tau is equal to half of lambda. I will now describe the computational ideas, which begin by rewriting optimal transportation cost as a dual problem, which is maximization over functions phi and psi. For the purpose of this presentation, it is not so important what this dual function looks like. But now if we look into the doubly entropic Wasserstein barycenter's objective, we can replace each transportation cost as a maximization over phi and psi as follows. Hence, at the end of the day, our problem is to find a saddle point of this Lagrangian L. And what is so special about entropic penalties is that whenever we fix any of the two variables, we can optimize this Lagrangian exactly in the third variable, which leads to natural schemes for finding saddle points. So one scheme is called iterative Bregman projections, which basically cycles through each of these variables and performs exact optimization steps. And this is known to be a very efficient procedure for computing lambda-lambda barycenters. However, if you take tau equals to a half of lambda, this numeric scheme becomes computationally unstable. And in fact, if tau is smaller than half of lambda, this scheme can be shown to explode as displayed in the plot in this slide. And we propose actually a very simple fix, which is to damp one of the exact maximization steps, where the damping factor eta, it depends on the ratio of tau and lambda. So in the case of interest, when tau is equal to half of lambda, the damping factor eta is equal to 1/2. And the main result of our paper is the following convergence bound. Here, the price to pay for damping is the factor 1 over eta, which again, in our case of interest, tau is equal to half of lambda. It means we pay a factor of 2 in our convergence bound. However, as I already explained in a previous slide, we actually gain a factor of lambda in approximation error. So whenever lambda is very small, this is a good trade-off to have. And beyond this result, we also consider an inexact version of this scheme, where the parameter psi can be updated with some error. And then we have essentially the same convergence bound up to the error of the updates. And this leads to some applications for computation of support-free barycenters. Thank you for your attention.
So, I do hope so that you enjoyed most of the presentations from the nominees for the Best Publication Award in the Artificial Intelligence Association event, AI Awards 2024 of Lithuania. And we will have the announcements on who was rewarded for the best publication and the best young scientist publication on the 9th of January, so basically in 2 days in Lithuania. We also will have the streaming of the event, and we really hope that this will inspire more and more colleagues and young scientists to have selection of the field of AI for the future studies, and we will have more stronger ecosystem in Lithuania. So thank you everyone who's joined and listened for the what is happening in the ecosystem of Lithuania, and have a good evening.